G'day, welcome back to Mathematics for my third and final video in the critical path analysis topic for HSC Standard 2 Mathematics. Today we're going to talk about network flow and cuts. Now your time is precious, so let's get straight into it and do some maths. Let's talk about network flow first of all. So network flow problems are looking at how much stuff we can get from one point to another point. Usually that stuff in these kind of questions will be things like traffic or water or mail deliveries, that kind of thing. Our starting point we refer to as the source of the problem, and the end point is called the sink. Now, we've got to think about how much stuff we can get through some of these vertices. Let's look at this point in the middle here, point C. Now, imagine this was like an intersection in a busy section of one-way roads. Now, out of this intersection, I can fit 55 cars here and 65 cars here. That's a total of 120. So 120 can get out. Let's see how much can get in. 45 plus 35 is 80, I believe. Yep. And then 80 plus 30 is 110. So if you think about it, we can get 110 cars into this intersection, but we can get 120 cars out of the intersection. That means the maximum amount of cars we can flow through this point is just the smaller of those two numbers, which is 110, okay? Even though these roads leading out can fit more, we can't get any more than that into the points, and so it's not an optimized vertex. That's the kind of things we're talking about in this topic. It is a bit strange at first. It's a type of mathematics you probably wouldn't have done in high school before, but hey, that's kind of why it's exciting. So the terminology here is that point there, C, it's got an inflow of 110 and an outflow of 120, and the maximum outflow is the smaller of those two numbers. So we're always limited by our smallest number in these questions, which in this case is 110. Okay, let's do a flow question. We have a series of pipes from a source S to a sink T, and the pipes are labeled with how many kiloliters of water per hour we can fit through that pipe. So this one down here is a massive pipe. It can fit 14 kiloliters of water. This one up here is a little one. It can only fit 5. Okay, we're going to analyze how much water we can get from S to T in 1 hour. So there's 3 paths going along here. There's the top path, middle path, and the bottom path. Let's look at the top path. Even though this pipe can fit 11, we can't send 11 kiloliters of water down this channel because we can't fit it through this pipe here, okay? This path shown here in red is restricted, just like before, by its smallest number, which is 5. So the only water we can send down this path up the top here is 5 because we can't fit any more in this pipe here. So we're just gonna write a 5 there. Across the middle, 11 and 14. So the only thing we can send through both channels is 11 because we can't fit more than 11 here. So I'm going to write an 11 there. And then the bottom channel, we are once again limited by our smallest number, which is 4. So the flow of the bottom path is going to be 4 kiloliters. So those are our 3 numbers. If we add them together, we get the total flow through the network in 1 hour, which happens to be 20. So when it's a relatively simple diagram and there's only a few possible paths, this calculation is not too complicated. Let's look at a complicated one just for fun. Here is a network diagram showing a system of one-way roads, and those roads are labeled with how many cars they can carry per hour. Now we're going to find the maximum flow from S over here to T over here. So let's just enlarge this a little bit. So there's a lot of different paths to get from S to T, and we've got to check all of them. Let's start off with this top path. Okay, across these 3 roads, even though this start and this ending road can fit a fair amount of cars, this one in the middle can only fit 180 cars. So down this blue path, we are going to send 180 cars in 1 hour. Okay, so 180 cars down SLMT. Now that we've done that, this road here is full. It can carry 100 cars, and we've just sent 180 cars. So we're going to, in this first road here, it could fit 240. We've just sent down 180. And the difference from 180 to 240 is 60. So there's still room for 60 cars on this road. Middle road here is blocked off. It can fit 180 and we've sent 180. So I'm just going to cross that out. And the one on the end, we're sending 180 and it can fit 220. So it's got room for 40 cars remaining. And now because I just sent 180 through the network, I'm just going to make a note of 180 over here and then hopefully not forget about it later. Okay, there is one path done. Let's look at the next one. Let's go across the top and then the middle here. So we're going to go SLNT, slint. It's not a weird word. It kind of sounds like a slur. Okay, so 3 options here. We've got a 60, a 160, and a 400. So the only amount of cars I can fit through all 3 of these roads, now that this first one is partially blocked, I can only send 60 cars down these 3 roads. So let's send 60 cars down SLNT. That now means this first road is blocked because we've filled up all 240. This middle road here still has room for 100 because we're sending 60 down. And this one here, if we take off 60, we still have 340 cars left remaining that we can fit on this road. All right, we send 60 down there, so we make a note of 60 and we proceed to the next path. Let's now go across the middle here and do S, P, and T, spint. Okay, across this path, we have a 260, a 140, and a 340. So the only thing we can fit on all three of those roads is 140. So let's send 140 cars down S, P, and T. That now means this first path has still got room for 120 because 260 take away 140 is 120. This middle path here now is completely blocked. We've sent all 140 down this path. And the one on the end, if we take 140 off the 340, we get 200 spaces remaining, I suppose you can think of it as. Okay, making a note of the 140 over here. And now we've got two more paths to get through this very, very tedious question. Let's go SPRT. Show me some spirit. Let's do it. Come on. Yep, thank you, PowerPoint. Okay, for these three roads, my smallest number is 120, so I'm going to send 120 down SPRT. That first road is now blocked. This second road now has room for 60 more cars, and this bottom road has only room for 30 more cars. Making a note of the 120 over here, adding to my tally as I go. And now for the last possible path across the bottom here, we can fit 250 on this road, but this road is almost full. It can only fit 30 more cars. So down this bottom path, we can only send 30 more cars, which now means we have 220 left here, and this one is now blocked. Okay, now that's all the possible options. There's no way of getting from S to T now without hitting one of these blocked roads. So we make a note of the 30, and now we are done. The total flow of this network diagram is the sum of these blue numbers, giving us a total of 530. Now, if you haven't noticed, that was very time consuming. It was very tedious, and there was a lot of room for error in me miscalculating one of these, 30 numbers that I just dealt with. So I bet you're thinking, there's gotta be a better way, and there is a better way, and it's with this thing called a cut. Let's talk about cuts. So a cut is a block in the network. It's like an imaginary line that separates the entire flow from source to sink. We usually use dotted lines. Here's an example of a cut that's blocking the flow from the source to the sink. Here's a bad example because it's not a cut. This is a line going through the network diagram, but it isn't entirely blocking the flow. I can still get from the source to the sink by going across the top here. Okay, so it's only called a cut if the imaginary line blocks off all the flow. Now, what we like about these cuts is before, with that big hectic question, as you were probably noticing, all of our calculations were always being limited by the smallest number in each path. So the aim of a cut is to just try and do a bit of clever trial and error to find all those small weaknesses in one go without doing all this tedious calculation. So it is quicker once you get good at it, but at the start it will just feel like a bit of trial and error. But yeah, it is easier than the method that we just looked at. It's much, much quicker. Okay, so cuts. Let's talk about the capacity of a cut. The capacity of a cut is how much flow it blocks. So all we have to do for that is count the edges that the cut is going through, and you'll see what I mean. Let's do a couple of examples. Here is a network, and there are a bunch of cuts here, and we're gonna find the capacity. So cut 1 is blocking this edge here and this edge here. 40 plus 70 is 110, and that's the capacity of cut 1. Now, where these get tricky is you only count flow that's being blocked from left to right, from the source side to the sink side. So when we're talking about cut 2, the 35 is all good, the 50 is all good because they're both going in the right direction. The 70 down here is all good. However, this line from M to W is flowing from right to left if you look at this arrow. Okay, so because that 80 is flowing from the right-hand side to the left-hand side, or it's going from the sink side to the source side, we are not going to count this 80. Because if you think about it, this 80 is coming from this vertex down here, which is W, and W has already been blocked by the line up here. Okay, so numbers going from right to left don't need to be counted, and they shouldn't be counted. So for cut 2, we're just going to do 35 plus 50 plus 70, which is 155. So keep an eye out for those because HSC questions will usually involve one edge that's going the wrong way, and you got to keep a keen eye out for it. Okay, cut 3, however, is all good. All 3 of these edges are flowing in the right direction. So 35 plus 50 plus 45 is, I just said that, is 130. And the last one is all good as well. 35 plus 50 is 85. Okay, over on the one on the right here, we have 3 cuts and we're going to calculate their capacities. For the first one, it's a no-brainer. All the edges are flowing in the right direction. So it's 310 plus 300 plus 150, which I believe is 760. Now for cut 2, this is a bit of a controversy, but we are not going to calculate the capacity of cut 2 because cut 2 is actually not a cut, it's an imposter. Because cut 2 is not blocking the entire flow of the network. We can still get around the bottom here and get from source to sink. So cut 2 is not a cut and we are not going to calculate its capacity. Cut 3 on the end is all good. All 3 of these edges are flowing from source to sink, so we can add all 3 of these together. 430 plus 190 plus 240 is equal to 860. Okay, now why we care about these cuts and their capacities is because this is the shortcut I was talking about. We are trying to find the cut that goes through all the weak edges in our network diagram. And then by adding together those weak edges, we find out the maximum flow of the network. The maximum flow is restricted by those small edges, and the cut is trying to find all of those. This leads into what's called the maximum flow minimum cut theory, and it's very simple. It's the easy way of finding the maximum flow of the network, which is what we did in the first 2 examples in today's video. All you've got to do is try and find the smallest possible cut in your diagram, and that will be your maximum flow, easy peasy. It usually only takes you a few trial and errors to find it. So as an example, if this was my network diagram and I was trying to find the maximum flow, I would just chuck a bunch of cuts on and I would calculate their capacities, and then whichever one is the smallest, which happens to be cut 2, has a capacity of 6 plus 5, which is 11. 11 is actually the maximum flow from the source to the sink in this network. Quick and easy. Didn't have to do all those recalculations and all those takeaways. Simple, simple, simple. Okay? So that's the main skill we're focusing on today, is being given a network diagram, trying to find the smallest possible cut, and that will be the maximum flow of the network. Let's do some examples. Here's a network diagram for oil pipelines, and we've got kiloliters per hour once again. There's already a cut on the image, and we want to find the capacity of the cut. Okay, so are they all flowing in the right direction? Yes, they are. All these edges are going from the left to the right, so they're all going to be calculated. The capacity of this cut will be 13 plus 15 plus 7, which is 35. Okay, let's find the maximum flow of the network by finding the minimum cut. It's probably not going to be the one that we just found because that would be very boring. The first 2 I always like to check when I'm doing a question like this is I check the one at the end, which is these 3 edges being blocked. I also like to check the one at the start. So from the source, if I block off all possible flow, I've got 16, 14, and 12, which is 42. So out of these 2, this one on the end is winning, 35. The question is, can we find a cut that is smaller than 35? And that may be our maximum flow. So some tips for finding this minimum cut, I'm seeing this diagram is primarily 3 paths. We've got the top path, the middle part, and the bottom path. Now, what's the smallest part of the top path? It is the 7. So I probably want to go through the 7. For the middle path, the smallest option out of 15 and 14 is 14, so that's probably going to be a good idea. And out of the bottom one, the smallest option is the 9. So if I draw a cut that goes up through here, cuts the 9, the 14, curves around and then hits the 7, would you believe that is actually going to be the minimum cut of this diagram? And here's the trick for this one as well. We are going to count the 9, it's going from left to right. We are going to count the 14, that's from left to right. The 7 is going from left to right, but if you look at the 3, okay, the 3 is coming from this dot here, and this dot is on the right-hand side of that dotted line. So the 3 is actually flowing from the sink side on the right over to this dot, which is on the left of the dotted line. So the 3 is actually flowing in the wrong direction and is not going to be counted. So the maximum flow of this diagram is just the 7, the 14, and the 9. We are not counting the 3. I hope that's clear because a lot of people struggle to see that. But once again, the 3 is flowing from a dot that's on the right to a dot that's on the left of the blue dotted line. Okay, so that cut has a capacity of 7 plus 14 plus 9, which is 30. And 30 is the smallest possible cut in this diagram. Don't worry, I checked, which means it is the maximum flow of this entire network from source to sink in 1 hour. There we go. So max flow, minimum cut capacity equals 30. So that's the skill. It is a bit weird at first, but we'll do a few more practice questions and then we'll finish off with one from an HSC exam. Let's do the next one. Next one, we have a network diagram showing flow from a central mail depot to a post office in Bulli. We've got a bunch of cuts on the diagram already, and it wants us to find the capacity of these 3 cuts. Okay, if you're getting it so far, by all means pause and have a think about these 2 questions, because then when I run through them on the screen, it's going to make more sense to you. And if you get them right, you'll feel really good. So that's always good. But there's your chance to pause. 3, 2, 1. Let's get on with it. Okay, cut A, all are flowing in the correct direction. We've got 5, 2, and 3, which makes 10 for the first one. For B, we have 3 and 2 and 4, and they are all flowing in the right direction. So that makes 9. And for cut C, we've got 3 in the right direction, 6 in the right direction, 4 in the right direction. The 1 is going from right to left. So the 1 here is not going to be counted. But the 4 and the 6 and the 3 together make a 13. So there's our 3 cut capacities. Part B, determine the maximum number of deliveries that can be made each day between the 2 depots. Okay, all that's asking us there is to find the maximum flow of the network. And if we know what we're talking about, when we're asked to find maximum flow, we just think, okay, sweet, let's just find the minimum cut. So let's see if you can find the smallest possible cut in this diagram. Like I said, it does take a bit of trial and error sometimes, and usually the questions are designed so you have to be a little bit clever to find the best one. Let's use my method again. Across the top, the smallest option is the 2, so I'll probably want to hit that. Across the middle path, 2 is definitely smaller than 6, so I want to hit the 2. And for the bottom option, the smallest option is either of these 2 3s. Maybe I can go up through this 3, hit this 2, go across and hit this 2, and then what do you know? That is actually the smallest possible cut in this diagram with a capacity of 3 plus 2 plus 2, which is 7, and that's actually the minimum cut, and that is therefore the maximum flow of this network. Okay, cool. Are we doing an example 4 or are we going straight to the HSC? Straight to the HSC. Beautiful. This one is from 2022. It's got a band 4 and a band 5 component. We have 5 main attractions in a wildlife park, and we have directional paths as shown. We've got source to sink, as we're used to by now, and the paths show how many visitors can access each path at any time. So it's all very straightforward so far. Okay, we have a cut on the diagram, and the first part for 1 mark is to find the flow capacity of that cut, and then part B is to find the suitable cut and explain why the maximum flow is less than 40. Once again, if this is making sense to you, please pause and have a think about this one yourself, because that's all the fun in these videos rather than me just yapping for 20 to 30 minutes. Okay, for the first one, let's check our directions. 10 is going in the right direction, 20 across the middle is all good. The 10 on the bottom is going in the right direction, but this 10 right here is flowing from the sink side to the source side, so that's the wrong way. So we are going to not count this 10. We're just going to have the 10, the 20, and the 10, which makes 40. Okay, now the question in part B is saying that the maximum flow is less than 40 visitors, and it wants us to find a cut that proves it. So there has to be a maximum flow or a cut capacity of less than 40. So let's see if we can find it. There should be a 35 somewhere, maybe a little bit of trial and error. Am I going to do trial and error? Let's check this one. Okay, this one has a 15 across the top, a 10 across there, a 10 across there, and this 10 is going in the wrong way. So this 10 is actually not going to get counted. That's really good news, because now when I do 10 plus 10 plus 15, I get 35. So I've found a cut with a capacity less than 40, and that must be the one that they're asking us to find. Okay, and they want us to actually draw on the diagram to find this. So you can do a bit of trial and error, you can bring your pencil, do whatever you need to do, but we're trying to find the 35 cut, and that's how we find it. Okay, so we have minimum cut of 35, and that means that is the maximum flow of the network. So we got that there. All right, that's actually a part C. One path is to be increasing capacity so that overall maximum flow will be 40 visitors at one time. Which path could be increased and by how much? Okay, so if we want to improve the overall maximum flow, we're going to have to improve one of these one of these edges on the minimum cut. So let's talk about this edge down here. Now we could probably improve this one because we've got 10 and 10 coming in, which is 20, and we've only got 10 coming out. But then we have to think about whether we can get more than that people to D. Let's look at this edge up here, AE. This looks like a good contender for me, because if you look at where AE is starting, we've got 10 and 10 coming into it, which is 20, but there's only 15 coming out. So 20 people coming in, 15 people coming out. Then if we look at where AE is ending, well, this vertex has got 15 and 10 coming in, which is 25, but it's got 10 and 20 coming out. So there's 25 coming in, but we could have 30 coming out. That's why AE is a really good contender for this question, because we've got 30 coming into the start of it. We've got the potential for 30 to come to out the end of it, but this one's only carrying 15 and 10. So we could up this one from A to E. We could up this to 20, and that would still work because we still have 30 coming in. We'd have 30 coming in here, and then we'd have 30 going out. So this top section would become more optimized if we increase 15 to 20. That's the band 5 part, because it does rely on you not just looking at these 4 edges, but looking at where they come from and seeing if there's potential to improve any of them. But A is a pretty good answer, and the justification will get you the 2 marks for the 2022 HSC question. Okay, that'll probably do it for this evening's video. Thanks so much if you made it through the end of that, and thanks again if you're subscribed. I appreciate that. If you're not subscribed, do better, I guess. But thanks for watching anyway, and I'll have some more standard maths revision videos coming out over the next term to get you prepped and ready for your HSC. So stay tuned to see those in your feed before too long. Bye for now, not forever. Take it easy.